there are three problems which are in the lead. It's 1.47, 1.78, and 1.92. So let's start from the top there, and I think we will have enough time to do all of those three problems, and if we have more time, I will just continue down the ranking list. So the first one, let's see, was 1.47. So it's a problem about space-time geometry and world lines. And the idea, well, there is a bit of flavor text here, but the idea, if we look at it, is that if we draw a Minkowski diagram here, and we have some intergalactic highway with a speed limit of u relative to this reference frame that I'm drawing here. So let's put the labels as well. And the spaceship passes at a velocity which is too high relative to this. So that's constant velocity. Let's draw that as a line in this Minkowski diagram. So this would be the world line of the spaceship that travels faster than this speed limit relative s. So we also have this intergalactic police, so that when the spaceship passes the police, which we can take to happen at this event A here, then the police starts accelerating in order to catch up with this speeding criminal. So constant acceleration in special relativity, that means that the world line of this police is going to be described by hyperbola, and the acceleration is going to determine the curvature of this hyperbola. So in essence, if we want to describe this world lines, let's see what we can do. So there are three questions. The first one is how long does the pursuit take according to the criminal, which is to say between the events A and B, what is the proper time along the red line, the red world line. The second question is how long does the pursuit take according to the police officer that is following this hyperbola, which is generally, of course, going to be a different time. And then the question is, what is the relative velocity between the police officer and the criminal at the end of the pursuit, so at the point B. We know what it is at the point A because that's given. It's a relative velocity of v. So let's see. So the first thing we need to do here is to describe the different world lines of the police and of the criminal. So the criminal is relatively simple. It's a straight world line, and the x variable is proportional to time variable, with the proportionality constant being the speed. So the criminal's world line is given by x equal to vt, and then generally we have some offset from x equal to 0 here. So I'm going to put plus x0, and we're going to discuss soon what x0 is. For the police's world line, then we have, sorry, is there a question? Someone is unmuted. So I'm going to, since that didn't seem to be a question, I'm going to take the liberty to mute that. So the police's world line, it's a hyperbola. which means that we have we have t squared minus x squared equal to something. And the question is what this something is equal to. And if we're going to have the correct proper acceleration, that is going to have to be 1 over the acceleration squared. So we can see that this has the correct units because acceleration is length per time squared. So since length and time with c equal to 1 have the same dimensions, acceleration has units of 1 over length. Which means that 1 over acceleration squared has units of length squared, which is the same as the dimensions on the left hand side. So we see here also that at t equal to 0, which is described by the x-axis, at t equal to 0, for the police we have minus x squared equal to minus 1 over a squared. So that means that the meeting event, the event A, which is an event on the x-axis, it's here, we have t equal to 0 and x equal to 1 over a. So the event where they meet is x equal to 1 over a. So if we also then look at the red world line here, we can insert this because we know that the criminal's world line needs to pass that event as well. So for the criminal, we have x equal to v times 0 plus x0, and that should be 1 over a for the event A. So that means that x0 is 1 over a. Okay? So now we know the world lines expressed in terms of the acceleration, and we know that they meet here in the event A. For the event B, we need to compute where event B happens. So what about event B? So for event B, we can use the fact that we know that both world lines must coincide. So both this formula and this formula must be true. So we can insert one into the other and see what we get. So for example, so let's write out here actually, this was vt plus 1 over a. So if I insert this x into this world line, let's see what I obtain. So let's keep t. So we get t squared minus, and then we had vt plus 1 over a squared should be equal to minus 1 over a squared. So I can take the left hand side here and expand this, and what we obtain is t squared 1 minus v squared. We get, let's keep minus 2 vt divided by a minus 1 over a squared, and that should be equal to minus a squared. So we can cancel 1 over a squared on both sides, and what we are left with is we can take out t, and then we're going to have t times t over gamma squared. Let's just write t, let's write it like that. T1 minus v squared minus 2v over a, right? And this should be equal to 0 because in the left hand side here we have a 0 left. So there are two options. to solve this equation. The first one is that t is equal to 0. That will give us back event A, which is indeed also a crossing of the world lines. The second option is that this entire bracket is equal to 0, which is going to be the case for event B. So for event B, we are going to have that t is equal to 2v divided by a 1 minus v squared. Okay? So let's actually, let's do this. Let's copy this to the next page. So we keep what we really wanted to remember. And we copy this as well. So for event B, we have this time. So that means that we can express now the difference in space-time between A and B. So we know the coordinates of both A and B, and we can create the space-time interval between them. So if we look here at delta t, that's, let's put a b there, that's tb minus ta, but ta was 0, so that's just equal to tb. So that's 2v divided by a 1 minus v squared. And similarly, we can express delta x, that's xb minus xa. xb was v tb plus 1 over a, and xa was v ta plus 1 over a. So what we can see here is that the 1 over a's cancel out, and we get v times the delta t. So that's v times delta t, which is not surprising because this criminal is traveling at a constant speed v, which is why we get v times delta t. But that's of course then equal to 2v squared divided by a 1 minus v squared. And if we now want to know the time elapsed, we can either use the space-time interval, so we could do delta s squared equal to delta t squared minus delta x squared. However, we know what that is going to result in. It's going to result in a time dilation formula. So what we can also do is to just take the tau, the elapsed time for the criminal, that's equal to delta t divided by gamma. So delta t divided by gamma, that's now 2v divided by a 1 minus v squared, and gamma is 1 over the square root of 1 minus v squared, so we have 1 minus v squared there, and we end up with 2v gamma divided by a. So this would be the result for a. Any questions? Yeah, so the question is, in the police's world line, why do we have minus 1 over a squared here? So if we look and compute the 4 acceleration, now I took this as something that I already knew, but if I compute the 4 acceleration, or the proper acceleration of this world line, that's going to be the proper acceleration is going to be given by A in this case. So if I compute the proper acceleration here for such a world line, that's what I will get essentially. So one way of doing that is to look just at the initial rest frame and see what the acceleration at t equal to 0 is, essentially. What dx dt is at t equal to 0. Or the second derivative. And it will turn out to be a. So that's why this looks like that. Anyone else? Because we like questions. Okay, so the second question, the B question, is how long does the pursuit take according to the police officer? So what we need to do is to compute this distance in space-time. So the way to do that is to note that the police world line that was given by exactly what we said there, it was t squared minus x squared is equal to minus 1 over a squared. So I can parameterize this using hyperbolic functions. So I will let t equal to, to 1 over a sinh a capital T, and I will let x be equal to 1 over a cosh, the same thing. So we see that this is just the parameterization of that hyperbola, just as you would parameterize a circle with the angle and the radius being in front. So this parameterizes the hyperbola, and it will turn out that we will see that t here, the capital T, is going to be the proper time of the police. So how can we do that? Well, we know that ds squared, that's dt squared minus dx squared, if we look at the infinitesimal proper time. So if we differentiate t here, so we get that dt is, when we differentiate sinh, we get cosh, and the inner derivative is a, so that a will cancel the 1 over a in front. So what remains is cosh a t times dt. Similarly, for x, we get that the x is sinh at dt. So if I square this, both dt and the x, and I take their difference, which is what appears here, what I get is cosh squared at minus sinh squared at dt squared. So now using the hyperbolic one, cosh squared minus sinh squared is 1, so this is just dt squared. Which means, of course, then that the proper time here of the police, that's exactly this curve parameter t that I introduced. So the question becomes, what is this t? Well, we know what that is. We have we have this expression. So for event A, which we saw here, both the capital T and the lowercase t are 0. However, at event B, we have the following. So we have that TB is 1 over A sinh A TB. And we know that TA, the capital TA, that was equal to 0. So the time elapsed for the police officer, so the delta T, that's equal to TB minus TA, which since TA was equal to 0, is TB. And TB I can solve from this equation, and what I obtain is 1 over A, the inverse of the hyperbolic sine of A TB. And the expression for TB we have here. We have already computed that. So just taking that from the previous page, and let's make it red just to show that this is from somewhere, means that this is 1 over A, the inverse hyperbolic sine of 2v divided by 1 minus v squared. So that's the final expression for the proper time experienced by the police. Any questions regarding that? So that's the result. Whoops. For, yeah. It is a general parameterization of this hyperbola, of this particular word line, yes. Of course, you could also, you could use whatever parameter you would like. I could instead use AT here as the parameter. That's fine. It still parameterizes the hyperbola. So if I would introduce here instead of AT, I could call this theta. Then here instead, I guess I would get something like d theta over a squared. So then I would have to take this into account there. Then the difference, the elapsed proper time would be d theta over a instead. But I kind of knew where I was going, so using the t here was more convenient. But if we look at this, so let's have a look at this form of the hyperbola in general, and look what the corresponding thing is in Euclidean space would be if you have something like x squared plus y squared equal to r squared. That's the equation for a circle, and most of you would know how to parameterize a circle. You would take that x is the radius times a cosine of something, and the y is the same radius times the sine of something, and that will be the general parameterization of the circle. Here it's essentially the same thing, but with the hyperbola instead. And the only thing to remember then is which you take the cosine, the hyperbolic cosine for, and which you take the hyperbolic sine for. And in order to get it correctly, you take the hyperbolic cosine for the parameter that has the same sign as the right-hand side. Then you have a general parameterization for the hyperbola. Okay, anyone else? Sorry, let me check. No, U is just the speed limit, right? So U plays no real role here because the police is initially assumed to be at rest. So that's why we can draw this hyperbola. So this hyperbola is going to have speed 0 here. So the initial speed of the police is assumed to be 0. The only role that U plays is that it's the speed limit relative to this frame. So that's going to correspond to something like that. So the only point here is that the criminal is speeding relative to that frame. So U plays no real role in the problem itself. So the police is initially at rest in that system. Okay, so regarding C, C is actually significantly simpler than both A and B. So the thing was that a priori I could determine this velocity by determining the forward velocity of the criminal there and the forward velocity of the police there in the same event where they meet, and I could take the inner product of that and get the relative gamma factor. However, we can reason for the result instead, and I will do that by going to an intermediate frame. So I'm going to take here, I'm going to take a frame that looks something like, let's see, it's going to look something like, it's actually the criminal's rest frame. So I'm going to see here if I can draw something that's remotely looking like that in here. So I'm going to take, that is the time axis, and that is the spatial axis. So this is the criminal's rest frame. So how is all of this going to look from that frame? Well, we can, let's have a look here. So what's going to happen is the following. So we have x prime, and we have t prime. So initially, in the criminal's frame, the criminal itself is going to be at rest in this frame. So it's just going to be this straight vertical line. However, if we look at the police officer, it's going to look something like this. Now, up to my drawing skills, of course. The point is the following. So the police is following a hyperbola in this frame, which means that the hyperbola, the hyperbola is the same hyperbola in all frames, which means that it's symmetric here around the x prime axis, which means that if I look at the event A, which we have over here, we have the event B here, the slope over here at B is going to be the same but inverted compared to the slope at A. So those two slopes are the same but with opposite sign. And that just follows from the symmetry of the space-time diagram around the x prime axis. So that means that the relative velocity at B, that must be the same as the relative velocity at A, or relative speed, let's say. It changes sign, of course. So let's put speed instead. So because of this, the answer to C is that the relative velocity is, the relative speed is v, the same as the initial relative velocity. So that concludes that problem. Any questions regarding that? Okay, no questions regarding C, then let's continue on. So the other two problems was 1.78 and 1.92. So let's see if we can find those. Yeah, so 1.78. I think we will have the time to conclude this before the break. So let me start right away. So the problem is the following. We have, let's take introduce our axis, so the x and the y axis. We take a pion, so a pion, and it's moving along the x-axis, so in the horizontal direction, and it has some energy E pi. And then at some point it decays, and it decays into a muon and a neutrino that has approximately zero mass. So the idea is here that we get a muon and we get a neutrino, and the muon here is moving off at an angle that is right against the direction of motion of the pion. So you have a right angle there, and the muon has an energy E mu, and the neutrino, in order to preserve momentum, must go off at some direction to the right. So the question is to calculate the energy E mu in terms of the energy E pi and the masses of the particles. So this is a problem where we can apply the conservation of form momentum. So if we call the form momentum of the pion P pi, we call the form momentum of the muon P mu, and we can call the form momentum of the neutrino P nu. The conservation of form momentum tells us that the form momentum before the decay is equal to the form momentum after the decay. So P pi must be equal to P mu plus P nu. Now, this is an equality between four vectors, so I can do any kind of manipulation that I could do between vectors also on this equation. So, in particular, I can see here that what I have information about and what I want information about is the muon in the rest frame, or rather in this lab frame. So, and I also have the information about the pion. I, however, don't have any information whatsoever about the neutrino. So that tells me that preferably I want the neutrino form momentum by itself. And I can accomplish that by subtracting the muon form momentum from both sides. So what I can do is subtracting the muon form momentum from both sides. I get P pi minus P mu equal to P nu. Now, given that, I can do the same operation on both sides. The particular thing I can do is to square this, to take the magnitude using the Minkowski metric on both sides here. So I can square this if I square the right-hand side as well. And we know now that the square of a form momentum is equal to the mass of the corresponding particle. So in particular, what's here on the right-hand side, the form momentum of the neutrino squared is equal to the mass of the neutrino squared. But we were told already in the problem that the neutrino could be considered to be approximately massless. So we're going to approximate that by 0. If we look at the left-hand side here, and we just expand this square, we get p pi squared plus p mu squared minus 2 p pi times p mu. The first two terms here, that's the form momentum of the particles squared, so that's equal to m pi squared plus m mu squared minus this inner product here. So before I write out what is going to be here, let me write out that inner product. So in the lab frame here, so in the lab frame, we had that p pi, that's equal to the energy of the pion, and then we have the free momentum of the pion, so p pi. Whereas we can write the same thing for the muon, is the energy of the muon and the spatial momentum of the muon. But we know that the spatial momentum of the pion was in the x direction and the spatial momentum of the muon was in the y direction. So this means that p pi and the Euclidean inner product with p mu is equal to 0 because they are orthogonal. So that means that if I take the inner product here, p pi times p mu, that's e pi e mu minus the inner product of the spatial momentum. But that was equal to 0. So what is left is e pi e mu. So that's what goes in here. So I get 2 times e pi times e mu. And this entire expression should be equal to 0. So I can solve here for e mu, and we'll see that that is equal to m pi squared plus m mu squared divided by 2 e pi. Okay, and that's then the result for this question. So that's the final result. Any questions on that? Yes, go ahead. Yeah. So the question is, why don't we have the mass added to let's see, to these quantities? So when we say that the pion has energy e pi, that includes the rest energy. So the total energy of the pion is e pi. If I would have said that the kinetic energy of the pion is e pi, then indeed I would have to add the mass. But if I just talk about the energy of the pion, that includes the rest mass, the rest energy. Yeah. Anyone else before we take a break? Okay, so if there are no further questions right now, let's take a break until 1:15. Yeah, sorry. Yeah, sure. The velocity of which particle? Right. So the question is, how would I write this in terms, if I wanted to write this in terms of the velocity of the incoming pion, then I would have to express, I can re-express this energy, this energy, the e pi. I can express that in terms of that velocity. So I know that that in general, so for a general particle moving, I know that E is equal to the mass times gamma, right? So this would be equal to m divided by the square root of 1 minus v squared. So in particular here I could insert this into this expression as well. So if I insert here E pi, so what I would get would be that E mu would be equal to m pi squared plus m mu squared divided by 2, and then I know that E pi is given by m pi and then divided by this square root, which means that the entire expression is multiplied by the square root, which would mean that I would get something like that. So that's how I would write it if I instead had the velocity of the pion. Okay, so it's basically 2 o'clock, so let's take a break there, and we'll be back at 1:15. Okay, so welcome back. I hope you had a good break. Looking at the vote that we had before the break, the next problem to be solved is this 1.92. So let's look at what we have. We have a pi meson, a pi zero meson, and we want that's a particle, and we want to know its mass. And it can be determined as follows, that you have this reaction, which is an interaction between a proton and a negative pion. And the result of that interaction is this pi zero plus a neutron. And the thing is that the uncharged pi zero meson, which is what we are interested in determining the mass of, it will very quickly decay into 2 photons. And it's difficult therefore to measure its mass directly. But we can measure the speed of the final neutron and use that to determine the mass of the pi zero, under the assumption that the proton and the pi minus are at rest relative to each other, and relative to the lab frame in which we are measuring the speed of the neutron. So if we just draw what we have a proton and we have a pi minus, and they are both at rest in the lab frame. That goes to this pi zero, and in addition a neutron. Of course, since the total spatial momentum is 0 in the lab frame, because both initial particles were at rest in the lab frame, the direction of the momenta, both the direction and the magnitude of the momentum of the neutron and the pi zero must be equal in magnitude but opposite in direction. So that momentum is still conserved. So what we can do here is very similar to what we did before the break. So I'm going to label the form momenta of the proton p pi, the form momenta of the negative pion by p minus, the form momentum of the neutral pion by p zero, and the form momentum of the neutron by pi n pn. Sorry. So again, we have the concept of conservation of form momentum, so conservation of energy and momentum, that tells us that pp plus p minus, which is the form momentum before the interaction, must be equal to the form momentum after the interaction. So that's p0 plus Pn. Now we have no information about the kinetic state of the neutral pion after the interaction. So what I'm going to do is that I'm going to try to eliminate that information from our equations by putting the P0 by itself and then squaring. So similar to what we did before, we subtract whatever is not P0 from the right hand side. So what we obtain is Pp plus P minus Pn is equal to P0. And then squaring that, we get P0 squared. And P0 squared, as we discussed, is nothing but the mass of the neutral pion. And that is what we want to know what it is. So if we look now on the left hand side, and I'm going to expand this, so I'm going to write here, I'm just going to write a capital P for Pp plus P minus. So if I write that here, I get P minus Pn squared, which is P squared plus Pn squared minus 2P times Pn. Now, if I look at what this capital P is, we are in the rest frame of both particles, which means that the momentum is 0, and the energy is just the sum of the rest energies of the particles, which is the mass of the proton plus the mass of the negative pion, and then 0 momentum. So that means that when I take P squared, I get Mp plus M minus squared. So that's going to determine this first square here. For the second square, that's the square of the form momentum of the neutron, so that's the neutron mass. And then the question is, what is the last term here? So if I want to express the form momentum of the neutron, I know that that's the energy of the neutron and then the spatial momentum of the neutron. So I can take the inner product here between the capital P and the neutron for momentum, and we get the time components multiplied by each other. So that's Mp plus M minus multiplied by En, and then minus the spatial components multiplied, but the overall momentum was 0, so 0 times whatever Pn is 0, so this is the result. However, I don't have En, but I do have the velocity of the neutron. And so we saw before already, before the break, how the energy is expressed in terms of the velocity. So we can just insert this here, and what we get is Mn, the neutron mass, times this Mp plus M minus divided by the square root of 1 minus Vn squared. So that expresses this inner product. So if I write out here, if I insert everything that I have, I find that this is equal to Mp plus M minus squared plus Mn squared minus 2Mn Mp plus M minus divided by the square root of 1 minus Vn squared. And since that should be equal to M0 squared, I can obtain the final result for the neutral pion mass by just taking the square root of this expression. So that would mean that m0, that would be this entire expression, so mp plus m minus squared plus mn squared minus 2 mn mp plus m minus divided by square root 1 minus vn squared, and then taking the square root of that. So this is the general expression, but we are also given some additional information. We are told that Vn here is a particular speed that one can measure. It's around 1 centimeter per nanosecond. So the question is, how does this compare to the speed of light? So let's look at that. So we have Vn is approximately 1 centimeter per nanosecond. In order to turn this into something more familiar that we can compare to the speed of light, we see that this is 10 to the minus 2 meters, that comes from the centimeters, divided by 10 to the minus 9 seconds, because 1 nanosecond is 10 to the minus 9 seconds. So if we do this, we get something like 10 to the 7 meters per second, which is significantly smaller than 3 times 10 to the 8 meters per second, which is the speed of light. So indeed we have that v here, the velocity of the neutron, is, well, at least 1.5 orders of magnitude smaller than the speed of light. So we can indeed look for just the leading order correction. So what is going to happen here is that I'm going to express, well, essentially this gamma factor, 1 over the square root of 1 minus Vn squared. So here, of course, in this expression, I have used c equal to 1, which means that if I want to recover the expression in terms of inserting the actual speed of light, this Vn here represents actually Vn divided by the speed of light. So in those units, Vn is approximately 10 to the 7 divided by 3 times 10 to the 8, which is approximately 1/3 times 10 to the minus 1, or if you will, 3 times 10 to the minus 2. So in natural units, Vn is 3 times 10 to the minus 2, which, to be consistent, we can also say that that is much smaller than 1. So what I do is that I take this square root, 1 minus Vn squared, and I can make an expansion of this around v equal to 0. So this would be 1 divided by 1 minus Vn squared divided by 2. This is approximately. And I now have 1 over 1 minus a small quantity, which I can further approximate by 1 plus that quantity. So 1 Vn squared divided by 2. So if I take this expression, this approximation, and I insert this approximation up here. Let's see what I get. So I take this entire expression, let's copy that, and let's paste it here. We got an extra 2. And I also take this expression, oops, not color, we're going to copy it, and let's paste it here. So I take this approximation for this term. What we find is that m0 is approximately mp plus m minus squared plus mn squared minus 2 mn mp plus m minus, and then multiplied by this approximation, so 1 plus vn squared divided by 2, and then the square root of everything. Okay, so what do we have? Let's look at that. So this is now equal to, if I look at these two terms and I look at the term with a 1 here. So the 1 is just multiplying the prefactor here. I can rewrite that as mp plus m minus mn squared. That includes all of the constant terms, so including this one. So that's just essentially completing the square here. And then I have the additional term, which depends on the neutron velocity, which is 2. Well, the 2 here cancels that 2. So we get, we get mn mp plus m minus, and then it's just vn squared, and then the square root of that. So this is the approximation in the small velocity limit. And if I really had that inclination, I could look up all the masses of the particles here, and I could determine the mass m0 in terms of all the other masses. So in particular, we see that if Vn would have been found to be 0, then the mass of the neutral pion, that would just be equal to this difference of the incoming masses and the neutron mass, which makes sense, because if it were like that, if Vn would be equal to 0, then you would also need to have neutral pion at rest in the lab frame, and then it would just be a question of conservation of the energies. Any questions regarding that? Okay, I hear no questions. So let's take one further problem. We have almost half an hour left. So let me have a look at the priority list. Yeah, so the next one in the priority list is problem 114, which is this cosmic ray muons. So muons produced by cosmic rays in the atmosphere. So this is something that we discussed yesterday as part of the experimental evidence for special relativity. So the idea, so let's just recap that, is that we are down here on Earth, and up in the atmosphere we have incoming cosmic rays. So we have cosmic rays that's going to hit the atmosphere, cosmic rays, producing muons. Essentially by these reactions, as we discussed yesterday. So the question is the following. So let's see. When the energy of the mu neutrinos, therefore the muons, is high enough, this ratio goes up. Blah 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 blah. So in the muons rest frame, the lifetime is 2.2 microseconds. And the speed of light is 3 times 10 to the 8 meters per second. And we are asked for the smallest energy of the muons, for muons which hit the ground before a substantial number of them decay. And the assumption here is that the muons are produced at the distance of L equal to 10 kilometers up in the air. We are also given that the rest mass of the muon is 106 MeV. So the question is, when does a substantial amount of these neutrinos hit the ground? So we discussed yesterday that the probability of a muon reaching the ground was essentially given by this exponential of minus the proper time elapsed divided by the muon mean life, and the muon mean life was given here in the problem. It was called T0 here. So let's put T0. So when do we say that a substantial amount of the muons hit the ground? Well, that's when this exponent becomes more or less equal to 1. So essentially when tau is equal to tau 0. So the substantial amount hitting the ground, we translate to tau approximately equal to the lifetime of the muons. So the question becomes, what is this tau? So as we discussed yesterday, the muons are going to be time dilated, so it's going to be essentially the time that elapses in the Earth frame, time dilated, so that's T divided by gamma. But T we can approximate, assuming that the muons travel very close to the speed of light, so T is going to be approximately equal to the distance divided by the speed, which is c. So that means that this tau is essentially L divided by c gamma. Okay, and this should be equal to tau 0. That was our how do you say? That's our condition for having a substantial amount of these muons hitting the ground. Okay, so I now have most of the ingredients, but the question was, what is the smallest energy of the muons? So essentially the energy for the muons where this is satisfied. So I can look at that. So the energy of the muons that's given by E equal to the muon mass multiplied by the gamma factor. So I can use this to express the gamma factor in terms of the energy and the mass of the muon. So just solving for gamma, I would find that we have gamma equal to E mu divided by M mu. So doing so, I can insert this expression for gamma into my expression for, into my condition. So if I do that, my condition turns into L divided by C gamma, and gamma was E mu divided by M mu equal to tau 0. Well, if I want to be consistent with my use of C here, I need to insert a C squared here, of course. So we let me do that. So if I insert the c, it becomes a c squared. The rest energy is m mu multiplied by c squared. So solving for the energy here, I find that E mu is equal to L m mu multiplied by c divided by tau 0. So we can check that we have the correct units. L over tau 0 has units of velocity, and energy has units of mass multiplied by velocity squared. So we have m multiplied by velocity squared. So that's consistent in terms of the units. And if I want to know what that energy is, I can just insert the values here of the input variables that I have. However, I would like to rewrite this as follows. I'm going to take L m mu c squared. I'm going to reinsert this c, and then c tau 0. And the reason that I do that is because this m mu c squared, that's exactly the rest, the mass of the muon multiplied by c squared. So that's going to be 106 MeVs. And then the distance divided by c tau 0 is dimensionless. So that's directly going to give me the correct units for the muon energy. So let's just do that. So we have 106 MeV, and then we have the length, which was 10 times 10 to the 3 meters, divided by c, which is 3 times 10 to the 8 meters per second, multiplied by tau 0, which was 2.2 times 10 to the minus 6 seconds. And we see here that all of the units cancel out. So we have 106 MeV, and then we have, let's count powers of 10. So we have 1, 4 upstairs, and we have 8, 2 downstairs. So we have 4 over minus 2, which is, it's 1 over 3 times 2.2 times 10 over 10 to 2, right? And this would then have to be computed numerically to get the actual result. But my point here is that you already have the correct units here. So if I just do that very quickly, that's actually approximately equal to 16 MeV, assuming that I did this correctly. That sounds small. I probably did something wrong. Let me rerun that. So it's 106 divided by 3 divided by 2.2. Ah yes, I must also multiply by 10 to the 2. So it's actually 1,600. So it's 1,600 MeV, or if you prefer smaller numbers, 1.6 GeV. Any questions regarding this problem? Okay, so we have 15 minutes left. So let me look at priority lists again. So there are a number of problems that have the same number of votes. So let me take problem 1137. That's the last one in the list of today. Right. So problem 137. So we are told that starting from Maxwell's equations and without assuming a particular gauge condition, we are supposed to show that the components of the electromagnetic field tensor satisfy a wave equation. So what we have here is Maxwell's equations. So we have d mu f mu nu is equal to j nu. And we are supposed to show that that this leads to the wave equation for each component. But we also have the other set of Maxwell's equations, which is epsilon nu sigma rho f sigma rho equal to 0, right? Okay. So let's try to have a look at that. And that should be without referring to the gauge conditions. So in general, let's see here. Right. So let's do it the following way. What we have here is, let's look at the left-hand side of this equation. So let me just write that down. That's d sigma f mu nu. That's the just the middle term written down, and I'm going to try to expand that. So I'm going to use an alternative form of this equation, which is essentially that, well, let me write that down. So let me move this down a bit, and let me then write down the alternative form of this. So the alternative form is that d mu f nu sigma, and then plus the cyclic permutations here. So d nu f sigma mu plus d sigma f mu nu is equal to 0. Now, I can of course erase all of the indices in this equation and it still holds. So if I do that, and I also pull those two terms to the right hand side, I get that the sigma f mu nu is minus d nu f sigma mu minus d mu f nu sigma. So looking at this term, I can replace this expression by the expression on the right hand side. So let's do that. This is going to be equal to minus, and then we have d sigma d nu f sigma mu minus d sigma d mu F nu sigma. We can now notice that F here, the field tensor, is assumed to be a smooth function, which means that I can change the order of those partial derivatives, both in the first term and in the second term. I'm also in the second term going to change the order of the indices of the field tensor, which, since the field tensor is antisymmetric, is going to give me a relative minus sign. So just writing that out, what I just said, let me start with the second term, or actually let me not, it will just be confusing. The first term is d nu d sigma F sigma mu, and the second term is a plus d mu d sigma F sigma nu. But now in both of those terms we have the divergence of the field tensor, which I can use the other set of Maxwell's equations to replace essentially this divergence by the electromagnetic current. So doing so, we obtain d nu, and then we have j mu plus d mu, and then the sigma F sigma nu is j nu. So just writing it a little bit nicer by changing the order of the terms, we have d mu j nu minus d nu j mu. And what we have here then must be this S mu nu that we had on the right hand side by definition. So this would be my S mu nu. So we have indeed shown that Maxwell's equations mean that the field tensor components satisfy this wave equation, where we have this source term S mu nu on the right hand side. And note here that this S mu nu is antisymmetric in mu and nu, and it must be that way because also the left hand side here is antisymmetric in mu and nu. If I change places with mu and nu, the left hand side changes sign, and so does the right hand side. Right, so that concludes the proof that indeed we can use Maxwell's equation to find that the components of the field tensor must satisfy this source wave equation. Are there any questions on this problem? Or any of the other problems that we have solved so far?